We want to now find what we call the roots of unity. Now, the roots of unity basically is dealing with a situation where we've got a complex number to the power of n, where n can be any number, positive number, positive integer, really, and that's equal to 1. Or in the case of where we're solving this equation here, it's n to the power of n minus 1 is equal to 0. So that's what we want to do. We're going to do it in here up to the 7th roots. And hopefully by that you get the idea of how do we actually go about it. Now, like most situations, when it's a small integer as such, it's pretty easy to find the roots through different ways. But then we'll show you a general way to do it. So for z squared is equal to 1, well, we know that the roots of this one is plus or minus 1. So if we plot these ones on the Argand diagram, what does it look like? Well, it looks like this. They're two vectors. Okay, one's going in this direction along the positive x-axis, and it goes 1 unit. The other one goes in the negative direction, goes 1 unit. So they're going in the opposite directions there, and they're 1 unit away from each other. That's all we need to do for that one. What about for z cubed is equal to 1? Well, we can do this one a number of ways. Z cubed minus 1, what we call the cube roots of unity. We can factorise. We get z minus 1, z squared plus z plus 1. That's our factorisation. So if we get the roots on, and we want to get the roots here and plot on the Argand diagram, we get z is equal to 1. So that comes from the first bracket. And then solving the second bracket, we apply the quadratic formula because it's going to come down to these roots. Minus 1 plus root minus a half plus root I root 3 on 2, and minus a half minus I root 3 on 2. In modulus argument form, we put those and apply those there. We get cis of 2 pi and 3 and minus cis of 2 pi and 3, or cis of minus 2 pi and 3 would be the same. It depends on which way we look at it, but it would be the same. That would give us the same angle there. So if we draw them up on the Argand diagram, what we're starting to see is, because it was z cubed equal to 1, the modulus of all this, so the modulus of this number here is 1. So everything ends up being at 1. So the modulus of all these three are 1 there. All it's differing is its angle. And if you notice the difference in the angles between it, and we're going to see this a lot more, the angle there is going to be the same. That's 2 pi and 3, 2 pi and 3, and 2 pi and 3. Hopefully we're noticing as well that our complex roots are appearing in conjugate pairs. So there's your conjugates. Minus 2 pi, cis of 2 pi and 3. Or you could write that as cis of minus 2 pi and 3 as well. That would give you the same point, same vector there. So keep that in mind. Find the roots of z to the power of 4 is equal to 1. Well, we can do this by factorisation as well. So z power of 2 plus 1 factorises down to that one, and z plus 1, z minus 1 factorises down to that one there. So we get 2 complex roots, 2 real roots, and along the Argand diagram it looks like that. That's what our vectors look like. That's what geometrically the 4th roots of unity look like there. So all along the axes, again, pi on 2, pi on 2, pi on 2, pi on 2. So distance between them all, the angle between them all is pi on 2. So, and again, our 2 roots there occur in complex conjugate pairs. So hopefully you can say that. So z to the power of n so far all have a root there at z is equal to 1. Because, well, 1 to the power of any number is equal to 1. So it's going to have 1 there. So they've all got at least 1 real root. Some have 2 real roots. Some have only 1. So, and all complex roots are conjugates. And the angle between all of them is 2 pi divided by n. So if you're not sure, go back and check. Squared and cubed and power of 4, but it's always 2 pi to the power of n. And that's the geometric application of it. All the roots are, all the moduli of all the of the 1, but they're spread like that. So what about z to the power of 5? Well, no nice factorizations here. What we need to do is apply de Moivre's theorem. Now, the idea here is that z to the power of 5 is equal to 1 and z some complex number. So if that's the case, we get the complex number to the power of 5. Now applying de Moivre's theorem, we get z to the power of 5, of r to the power of 5 is our modulus, and we get cos 5 theta plus I sine 5 theta. Now, the modulus of z to the power of 5, which is the modulus, there's the modulus there, is equal to 1 cis whatever there. So the modulus is 1, so that means the modulus of z is 1. So every complex number here has a modulus of 1, which we just talked about in the other ones, and we saw that's what the roots look like. Now, we can write 1 to the power of 5 as this. So cos of 5 theta plus I sine 5 theta is equal to 1. So if it's equal to 1, well, 1 can be written as 1 plus 0i. So if we equate the real and imaginary parts, cos of 5 theta would be equal to 1, sine of 5 theta is equal to 0. So there's our real and imaginary parts. Now, what we want to do is, what's the value of 5 theta that makes cos of that angle equal 1 and sine of that angle equal 0? Now, in our general terms, we know that will only occur when we're at the positive x-axis. So we're at the positive x-axis when we get 2 pi and multiply that by some integer. So 2k pi, so any integer, would give us a position on the positive x-axis every time. So every time we multiply by an integer, it'll go around 2 pi. Or even a negative integer, we'd go back the other way. So it would still work in that case. So theta then would be equal to 2k pi divided by 5. So we can get our 5, we know there's 5 solutions because it's z to the power of 5, means we're going to get 5 solutions there. So if we substitute 5 numbers in there, and we can substitute any 5 numbers and we'll get 5 unique solutions. But what the simplest ones are 0, 1, 2, 3, 4. That's the simplest numbers to put in. If we put those in, we start to get our solutions. Now, if k is equal to 0, theta is equal to 0. Okay, so if theta is equal to 0, we know z is equal to 1. Or cis of 0. Okay, if we want to put it that way. We know that we're going to get a root at 1. If k is equal to 1, then theta would be 2 pi and 5, and z would be equal to cis of 2 pi and 5. So there's another root. K is equal to 2, we get 4 pi and 5, which means the angle there, the complex number would be cis of 4 pi and 5. K is equal to 3, we know theta would be 6 pi and 5. We get the complex number of cis 6 pi and 5, which we've written, again, check out where 6 pi and 5 is. It's the same as cis of minus 4 pi and 5, which I write it like that because it's going to be in the principal argument form. But also, if we're noticing, oh wait on, we're getting complex conjugate roots, which means the next one should be cis of minus 2 pi and 5, which does work out because when k is 4, theta's 8 pi and 5, and cis is 8 pi, we get cis of 8 pi and 5, which is the same as minus 2 pi and 5. They're in the same positions, just that these are written in its principal argument form. What does it look like? There's what our diagram looks like. There's our geometric representation. Everything's got a modulus of 1, which means we can draw a circle there, if I'm doing it a little bit more neatly, or missed it there. So it comes around there. This can be represented by a circle because all values there of the moduli are 1. And then, as we said before, we've got the same distance between those angles there. So 2 pi and 5, and then it goes around to 4 pi and 5. Then it was 6 pi and 5, which we said we could write as minus 4 pi and 5. Then round to 8 pi and 5, which we said also is minus 2 pi and 5. So there's our 5 solutions, equally spaced around a unit circle, and the roots are complex conjugates. If they are complex, z equals 1 is completely real. So the other two are complex conjugates. So there's how we get to start to draw it up. So drawing it up's pretty easy if we remember that. It's going to be around a unit circle with equally spaced arms there at 2 pi on n. In this case, n was 5, so 2 pi on 5. So we can do that same idea with the roots of z to the power of 6 is equal to 1. So if that's our idea, we know the modulus is going to be 1. So each modulus of each arm would be 1. And the argument will be 2k pi on 6. Now you can prove it using the de Moivre's theorem. You can go through and do that, and like we did in 5. But this is a legitimate way to do it because we know this would be the situation. So it means that roots are going to be equally spaced at k pi on 3 because the 2 and the 6 cancel. We substitute 6 values in because we're going to get 6 roots. So when we get 0, okay, we get cis of 0 or cis of 2 pi. Either way, it's the same position. Put in 1, we get cis of 2 pi on 6, which is pi on 3. Cis of 2 pi on 3 for the third one. Cis of pi. Notice all these roots are going up by pi on 3. Or if we're going from 0, we're going back by pi on 3. To give us those 6 equally spaced roots around a unit circle. Pi on 3, pi on 3, pi on 3 between each of them. Okay, which is 2 pi on 6 between each of them. The roots are occurring in complex conjugate pairs, which makes life very nice for us. And what about the 7th roots of unity? So we know if it's z to the power of 7, we get 7 roots equally spaced around the unit circle, 2 pi on 7. So there's our roots. This is 2k pi, where k is 1, 2, 3, 4, 5, or 0, 1, 2, 3, 4, 5, 6. And they're not all there. But here they are. When we put 0 in, we get that one. When we get 1, put k is equal to 1 in, we get 2 pi on 7. Put 2 in, we get 4 pi on 7. 6 pi on 7. 8 pi on 7, which is minus 6 pi on 7. 10 pi on 7, which is minus 4 pi on 7. 12 pi on 7, which is minus 2 pi on 7. And more importantly, there's our diagram. Here's our roots at 1 unit away from the origin and pi on 7. 2 pi on 7, sorry. Angles equally spaced there. So again, complex conjugates are occurring all the time. So that's what we're looking at with the complex roots of unity. How we do it, some easy ways to do it, some harder ways to do it. You can choose whichever you like, or be prepared to say do it whichever way the question would want you to do it.